This video series goes through the daily problems in this maths calendar that is published by the American Mathematical Society. You can either purchase it through their website or via Amazon. Today's question is, what is the order of the symmetry group of a regular heptagon? A heptagon is a seven-sided polygon. Being regular means each of its side lengths is the same, and thus the angles are also the same. The order of the symmetry group is basically asking how many different symmetries of the regular heptagon are there, and on the next page we will define what a symmetry is of a shape in R2 in the two-dimensional plane. There are a priori two different definitions that are of interest, but it turns out that they are actually equivalent definitions. A rigid motion of the plane is a transformation of the plane which does not change distances. Examples are translations, shifting everything up or down or left or right, rotations, picking a point and rotating everything about that point, and reflections, drawing a line and reflecting everything in that line. It turns out that every possible transformation that preserves distance can be made from a composition of these three basic rigid motions. In fact, more can be said. Every rigid transformation can be made out of just three reflections. It's often conceptually easier, though, of thinking in terms of these three types of rigid motions. If we draw our shape, such as our regular heptagon, on the plane, and if we can perform a rigid motion of the plane, such that afterwards, when we look at it, the heptagon looks identical to when we first started, that would be a symmetry of the heptagon. To emphasize, the final image must end up on top of the original image. For instance, we can take our heptagon and we can rotate it about its center, and if we rotate it by just the right amount, it will end up overlapping its former image and thus forms a symmetry. So the first definition is in terms of transforming the whole plane in such a way that our shape gets mapped back onto itself. The second definition largely ignores the plane, although of course the plane is used to define distances. The second definition simply looks for a mapping of the shape onto itself. So if we have, for example, this triangle here, then we want a mapping that will tell us, given any point on this triangle, where does it get mapped to. An example of a mapping would be one that sends this vertex here to this vertex, sends this vertex here to this vertex, and sends this vertex here to this vertex, and sends this point on the side to this point, and this point to this point, and this point to this point, and so forth. The function that does this mapping must preserve distance if it is to be of interest to us. So this blue point down here, if it were 1 centimeter from this vertex here, then if this vertex gets mapped to this vertex, this point must get mapped to a point which is 1 centimeter away, so that distances are preserved. Precisely, the distance between any 2 points must also be the distance between the image of those 2 points under our transformation. If we can come up with a mapping that preserves distance and maps our shape onto our shape, so it's a one-to-one and onto mapping, then it is a symmetry. Clearly, any rigid motion of the plane which leaves our shape invariant gives us a mapping of the shape onto itself. We simply take our transformation of the plane, which is a function from R2 to R2, and we just restrict it to the shape. We just look at what it does to our shape. So this definition is a special case of this definition here. It turns out that there are no other possible transformations of the figure into itself that preserve distance that cannot be obtained from a rigid motion of the whole plane. Or in other words, given any such transformation of our figure, we can always extend it to a rigid motion of the whole plane. Therefore, these two definitions are equivalent. We can choose to work with whichever one we find more convenient for the problem at hand. A little bit of thought shows that any symmetry of an n-sided polygon, abbreviated n-gon, must send a vertex to a vertex. For example, no symmetry of the triangle could send this vertex into a point on the side of the triangle. Intuitively, this is because a vertex looks nothing like a point in the side of a triangle. Rigorously, this can be proved as follows. Consider a point near the vertex on one side and another point the same distance from the vertex on the other side. Because the transformation preserves distance, these two blue points must be mapped to points on either side here that are the same distance. So the distance from here to here and the distance from here to here must be the same, and the distance from here to here and the distance from here to here must be the same. Now, we don't know whether the point here gets mapped to this point or this point, but whichever one it gets mapped to, the other point has to get mapped to the other point because distances are preserved. So if two distinct points get mapped to the same point, that means 2 points that are a certain distance apart get mapped to 2 points that have zero distance between them, which contradicts the fact that our mapping preserves distance. We now arrive at a contradiction. The distance between these two blue points in the image is going to be greater than the distance between the original 2 points. Indeed, we have a small triangle here, and the distance between the original 2 points is the length of the base of the triangle, and the distance between the 2 blue points in the image is the sum of the other 2 sides of this triangle. And we can see and we can prove that the distance going along the other 2 sides of the triangle is strictly greater than the distance along the base. By a similar argument, at least for regular n-gons, adjacent vertices must be mapped to adjacent vertices. So for this 6-sided figure, if this vertex is mapped to this vertex, then an adjacent vertex, which, at least if the n-gon is regular, an adjacent vertex will be the closest vertex to this one. So this vertex here cannot be mapped to a vertex that is not adjacent to this one because it will be further away. These observations quickly lead to a way of finding all possible symmetries of a regular n-gon. Specifically, given a regular n-gon, we just have to pick 2 adjacent vertices, call them A and B. We know that any symmetry must send both A and B to other vertices, and moreover, it must send them to adjacent vertices. We now simply ask how many possible choices are there for where A goes and where B goes. For vertex A, it can go to any vertex, including itself, which we'll come to in a second, and so there are n choices because there are n vertices. B must be sent to a vertex which is adjacent to where A was sent, so there's only 2 choices for B, and that means in total there are 2n symmetries. One of these symmetries will just send the n-gon directly into itself. Every vertex will be sent to itself. But in terms of what the original question is asking about the order of the symmetry group, we include this identity transformation in the count. So the final answer for today's question is for a regular heptagon, which has 7 sides, the order of the symmetry group must be 2 times 7 or 14.